Camera off.
All right. So thanks to Gabriel for the invitation to give a Phys 10 talk. It's a real honor and a real pleasure. And thank you to all of you for coming out. So I hope this will be interesting and enjoyable. So on the bottom right of your screen there, you should see a picture of Einstein. So he's obviously one of our most celebrated thinkers, most celebrated thinker in human history. And he's in our discipline. Yay, physics. And so, I feel that, every physics major should know what Einstein said, right? Have at least a gist of the idea. Now, of course, you'll get some special relativity in Phys 263 and in your E&M courses and so on. But most of you, or you won't see general relativity unless you take Phys 476. And then you'll see a little bit. I mean, general relativity is a big subject. One course in general relativity is not a lot. Right. So, for sure, as physics majors, I feel that, you should have sort of the gist of what Einstein said in general relativity, whether you take 476 or not, or especially if you don't take 476. What I'm hoping is that this kind of a presentation will give you just sort of an intuitive feel for what general relativity is all about. And, as physics majors going out into the world, I think you should have like a better sort of understanding or explanation of what Einstein said in general relativity than the ball on the rubber sheet analogy. All right, so let's get going. There's lots to cover here. So I guess maybe the first thing to say is, nature is deeply mysterious. And in order to unravel nature's mysteries, we really need to have a lot of imagination. We really need to be able to think outside the box. There's an Einstein quote here, imagination is more important than knowledge. And that's really important. Okay, so now, of course, what we're going to do is we're going to replace Newton's model of gravity with Einstein's model of gravity. But before we start, bashing Newton, let's actually celebrate a little bit the genius of Newton. Okay, so genius of Newton, and he certainly was a genius. Okay, so so the first thing is here is the Earth. And you're standing on the Earth like this. So I hope this is all clear and everyone can see this. So you're standing on the Earth and you're holding this this ball or this rock or whatever. And it sure feels like there's a force of gravity pulling down on that rock. Okay? When you let that rock go, it accelerates down. Why was the force of gravity pulling it down, making it move faster and faster down? Okay, and then you notice that, if I throw the ball sideways a little bit, give it some initial velocity to the side, well, it'll go a little ways, but it'll fall down. And on this parabolic trajectory, whatever, you throw it a bit harder, it'll go a bit further before it comes down. But if you throw it hard enough, then it's going to orbit around the Earth. So it'll be in a low Earth orbit. And the speed, the horizontal speed you'd have to throw it with, is about 8 kilometers per second. Okay, and then it will be orbiting around the Earth. And now, people have, wondered for a long time, well, we've got the moon, which is this, big rock orbiting around the Earth. So what's causing that? And so the idea is we've got the moon up here, and the moon has some horizontal speed. It's about 1 kilometer per second. And the moon orbits around the Earth, just like this rock was orbiting around the Earth. Okay, and so in order for, Newton had figured out dynamics. He knew that, well, there's a centripetal acceleration towards the center of the Earth, and and you need a force to cause that centripetal acceleration. What could that force possibly be? Well, look, I'm holding onto this rock, and the Earth is pulling the rock down towards the center of the Earth. It's exerting a force on the rock towards the center of the Earth. So maybe, just maybe, the force of gravity, reaches all the way up to the moon and grabs onto the moon and exerts a force towards the center of the Earth, causing this centripetal acceleration. So there's this force of gravity reaching from the Earth all the way up to the moon, and the force of gravity divided by the mass of the moon, and that'll be the acceleration of the moon. Okay, and so then Newton did some calculations with knowing something about the orbit of the moon, and he figured out that yes, this force of gravity has to be an inverse distance squared force. So it decreases in strength with the distance squared. Okay, and it's directed towards the center of the Earth. Or you can generalize this to any two bodies. So any two bodies, they exert gravitational forces on each other, which are inversely proportional to in strength to their distance squared. Okay, so this was fantastic. This was amazing because really what Newton did is he really connected, heaven and earth with this thought experiment. So, prior to this time, there was this sort of separation between, stuff that happens on the earth, those, that obeys certain laws and so on that were being developed. But the stuff that happens out, out in the heavens, so to speak, those obey different laws. And Newton showed, no, same laws. Okay, so what applies down here applies out there. And so there's universality to this. Okay, so so this inverse square force law explained everything. I mean, it was astounding. Okay, so it explained the orbits of the planets. It explained Kepler's three laws, that planets orbit on ellipses. It explained the area law. It explained the period law. It explained this age-old mystery, the precession of the equinoxes. It explained the tides. It just explained an enormous amount of stuff. So Newton's Principia was an absolute tour de force, like the world had never seen. Okay, so it was an enormous success. The Principia is, probably the most influential scientific publication in human history. Okay, so Newton was a genius. Great. So, but then there's some problems. Okay, so first of all, first problem to arise arose immediately. Okay, so people wondered about this mysterious, invisible force. That reaches from the Earth through the vacuum of empty space to grab onto the moon and pull it down towards the Earth. Okay, and serious scientists at that time, they accused Newton of bringing the occult back into science. Okay, and so here's a quote of someone at that time. So I want you to listen carefully. That one body, say the Earth, may act upon another, say the moon, at a distance through vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity, that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Okay, so the idea of this mysterious invisible force, so people were used to contact forces. Yeah, I can understand that. This mysterious sort of action at distance force, it was a problem. So who said that? Isaac Newton himself. So Isaac Newton himself was fully aware that this was weird. Okay, but he said furthermore, he said, I have not yet been able to discover the cause of these properties of gravity from phenomena, and I feign no hypotheses. So I'm not going to make stuff up. It is enough that gravity does really exist and acts according to the laws as I have explained them, 1 over r squared central force law. And it abundantly serves to account for all the motions of the celestial bodies. Okay, so, but anyways, the point here is that even Newton himself knew that there was a problem right to begin with. Okay, and so scientists after that tried to find more concrete models of gravity and so on. Those all failed. Okay, then the second thing started happening in around the 1850s, and it was discovered that Newton's force model of gravity fails to satisfy experiments. Okay, so Newton's force model of gravity predicts that if this is the sun, then and this is Mercury, then Mercury will orbit around the sun in an elliptical orbit and retrace its steps over and over again. Okay, but when you actually take out a telescope by the 1850s, telescope technology had improved to the point where you could see a slight discrepancy. Actually, what happens is the Mercury orbits on a trajectory sort of like this. So it's an elliptical trajectory, but the major axis of the ellipse precesses like this. The precession is very tiny. Actually, most of this precession is due to the perturbation from other planets, but still, when you add everything up, it didn't quite add up. There was a little bit more precession than was predicted by Newton's theory. So Newton's theory failed experiment. Okay, so then other ideas were put forward. Maybe there's another planet. Let's call it Vulcan. which maybe is causing this extra perturbation and so on. But at the end of the day, that failed. Okay, the third thing to note is that Newton's model of gravity fails theory. And so here we're talking about 1905. Einstein's, discovered that there's a speed limit in the universe. If you look at this law, F gravity is gm1 m2 over r squared. There's no mention of time in there. This is a weird. This is a weird. Someone has their microphone unmuted. I think it's maybe Sarah. Sarah Shaw. Yeah, so there's no mention of time in there, and so it's this weird action at a distance, instantaneous action at a distance, which violates the universal speed limit, speed of light. Okay, so anyways, there's lots of motivations for Einstein to start looking for a new model of gravity. Okay, so let's look at that. Let's jump into that right away. All right, so here is what we're going to do. We're going to do a very, very simple experiment, and we're going to imagine, so this on this side of the page is going to be Newton, and on this side of the page is going to be Einstein's wave. Okay, so we're going to imagine a very simple thought experiment here. And the thought experiment is there's a ladder. Let me just get this spacing right here. So there's a ladder. And Alice climbs to the top of the ladder, and she just steps off the ladder and free falls down to the ground. Okay, that's our experiment. I love these thought experiments. They're so deceptively simple. Okay, so what we're going to do is we're going to take pictures of Alice as she falls down the ladder. So here's our first snapshot. And this snapshot is taken at t equals 0. Okay, and then we take another snapshot at, say, t equals 1 second. And we're going to lay these snapshots out side by side. T equals 1 second. And then we take a third snapshot at t equals 2 seconds. And let's suppose that it takes Alice exactly 2 seconds to, when she steps off the ladder, to free fall down and hit the ground. So in the last snapshot, she's at the bottom. Ouch, right? Okay, so now the key question here is in this middle snapshot at exactly the half-time point, where is Alice on this ladder? Is she here at the halfway point down the ladder? Is she further down the ladder? Is she less far down the ladder? Well, obviously she's less far down the ladder because if gravity is this force pulling down, then it's causing an acceleration, causing her speed to increase. Then during the first half of her fall, she will only fall a small distance. During the second half of her fall, she will fall a greater distance because her average velocity in the second half of the time interval is greater than in the first half. Okay, so we have these 3 dots, and we're going to connect these dots. This, and this is, of course, a parabolic trajectory. There it is. Okay, and so what we've drawn is a graph. Well, what are the axes for this graph? Well, along this axis, we've laid the pictures out, 0, 1, 2 seconds. We've laid them out in time, t, okay? And on this axis, we have Alice falling through space, one vertical dimension of space, the z-axis or whatever. Okay, so this axis is a space axis. So this is a 2-dimensional space-time, one space and one time dimension. And so we can see that in this, that Alice's path through space-time, her path through space as time goes on, is this curved path. Okay, so now we can understand this path as follows. So Newton would think as follows. This is A for Alice. This is Alice's free fall trajectory through space-time. So the first thing we do, that Newton does, that all of us do, is we assume, this is very important, we assume that Alice is accelerating down. Okay? So acceleration down. So I'll draw a down and up arrows for down and up. Okay, so we assume that Alice is accelerating down. Sure looks like she's accelerating down. Okay, so if Alice is accelerating down, well, we know Newtonian dynamics, F equals ma. So there's an acceleration down. There must be a force down. right? So this implies, so a double arrow like that, it means implies, is equivalent to the statement that there's a force acting on her while she's in free fall, and that force is down, okay? And so that would cause one, Newton, to invent a force of gravity down. Okay, so we invent the force of gravity down. We are inventing this thing, force of gravity downwards. And also, I want you to notice that associated with this downward acceleration and this downward force is a curved trajectory. This is not a straight line, it's a curved line. Okay, so this is the same thing. Acceleration down and force down are associated with curve down. So curved down. Okay, I hope everyone can see this relatively clearly. Okay, so I want to point out also that this fact, the fact that in the middle snapshot, Alice is not in the middle of the ladder, she's above the middle of the ladder. Okay? That is explained by gravity being a force pulling down. Okay? As we talked about. So this is a key observation that we're going to return to. So key observation. Okay? And it happens because as a force pulling down, causing the velocity to increase. That means her average velocity is less during the first half of her fall than during the second half of her fall. She covers a greater distance in the second half of her fall than in the first half of her fall. Okay, so we can explain this key observation by thinking of gravity as a force pulling down. Okay, great. So now let's suppose that we've got Alice who climbed up the ladder and stepped off and free falled down to the bottom. Okay, and suppose we've got Bob standing at the bottom. He's holding the ladder vertical for his sister Alice. Okay, so this is Bob. In the first snapshot, he's at the bottom of the ladder. In the second snapshot, he's at the bottom of the ladder. In the third snapshot, he's at the bottom of the ladder. So his path through space-time, if we connect the dots, is as time goes on, his position doesn't change in space, and it's a straight line. Okay, so Bob, give him the letter B. So Bob, first of all, let's look at the forces that are on Bob. There is a normal force pushing up on Bob. The ground is pushing up on Bob. A normal force pushing up. That is obvious and real. Very important. This is a real force. Okay? If Bob were to be standing on say a spring, well, then that spring would be compressed. A compressed spring is obviously pushing up on him. Okay, so there's definitely a force pushing up on him. But wait a minute, we've invented this gravitational force pulling down. Okay, so plus a force of gravity pulling down. And that normal force is exactly equal in magnitude to the force of gravity pulling down, and such that they cancel out. So then we get the net force, the sum of all the forces is equal to 0. And according to basic Newtonian dynamics, if the net force is 0, that's equivalent to the acceleration being 0. Okay? And this acceleration being 0 is also an assumption. It agrees with our earlier, it's consistent with our earlier assumption. We are assuming that when someone is standing on the ground, they're not accelerating. It's when you're in free fall that you're accelerating. Okay? These two assumptions, this one and this one, are connected to each other. Okay? They're the same assumption. Okay? And moreover, you'll notice that the idea of when you're accelerating down, force down is associated with the path being curved down. Here we have force equals net force equals 0, acceleration equals 0, and that's connected with a straight path through space-time. Okay, so it's straight. Great. So this is how Newton would think about this situation, and it all makes sense, and we're all happy. Okay. Now, in order to get to the way Einstein thinks, we need to take an intermediate step. What we're going to do is we're going to talk about this example of Alice in free falling down, and Bob on the ground here. We're going to talk about this same idea in a slightly different context. So we're going to imagine that there is a box, a closed room. There is a closed room, and it is sitting on the surface of the Earth. okay, E for Earth there, and you are inside this box, sitting at rest on the surface of the Earth. And what are you doing? You are holding a mass in your hand. You're holding a rock in your hand, okay? So there is obviously a force on that rock in the upwards direction, okay? The normal force coming from your hand, okay? And that force is clearly real. We're going to try to distinguish between real forces and fictitious forces, okay? So this normal force is clearly real. If you're holding a bowling ball for like 10 minutes, you'll know that that upward force that you are applying to the bowling ball is real, okay? But then we say, but this thing is not accelerating. We assume that the ball is not accelerating, that the acceleration is equal to 0, okay? And so in order to explain what's happening, well, wait a minute, if the acceleration is 0, the net force has to be 0. So we invent this gravitational force pulling down in order to balance the normal force pushing up that's real. So we invent force of gravity pulling down. And that balances out, acceleration is 0, great. But then when we release this ball, just let go, then this ball will have a force acting on it while it's in free fall. And that force pulling down is going to cause an acceleration downwards. Okay? So again, we say, yeah, that's right. It's accelerating down. So we're assuming that when it's doing what it does, that's acceleration down. Okay? So everything is fine. Now we shift over to Einstein's point of view. And so here's where we come into this thing called the equivalence principle. So 3 lines like that is like an equal sign with the third one equivalent. Okay, so this is the equivalence principle. Okay, equivalence principle. So what Einstein says is, you know what? I'm going to suppose that, during the nighttime, you go to sleep in your little room, and unbeknownst to you, I'm going to take your room off of the surface of the Earth, and I'm going to put your room and you and everything in it, I'm going to put you out into the middle of empty space. Okay, and so there is super important here. There are no gravitational forces anywhere in this picture. Okay, and what I do is I attach a little rocket thruster to the bottom of your room, and I turn it on such that your room is accelerating up with an acceleration g, 9.81. Okay, and then you wake up in the morning and you do the same experiment. You say, yeah, I really like that experiment. It's really interesting. I was holding this bowling ball out and pushing up, and it got really hard after a while. I'm going to do that same experiment. Okay, so you pick up the bowling ball, and what you notice is nothing. Nothing's different. Okay, and so why is that? So you're applying this normal force up. And why is that? Well, first of all, this ball in this situation, it is true. Another room here. It is true that this bowling ball is accelerating, has an acceleration equal to g up. Okay, and in order to cause that acceleration up, so the room and you and the ball are all accelerating up with an acceleration g. Well, in order to cause that ball to accelerate up with an acceleration g requires a force on it in an upwards direction. Okay, and that's that normal force that you're applying with your hand upwards. Okay, so that true acceleration is associated with a true, real normal force upwards. This is a real force. Okay, great. And then you do this same experiment. You drop the ball. Okay, you remove your hand, and then what happens is the ball, from your point of view, it looks as if the ball is accelerating down. But in reality, what's true about this ball is that the acceleration is equal to 0. While you are applying this upward force, this ball is accelerating upwards along with you and the rest of the room. The instant you remove your hand, the force on this ball is 0. Remember, there's no gravitational forces anywhere in sight. All of a sudden, this ball now starts moving with a constant velocity. Oh, but wait, the room continues to pick up speed faster and faster and faster. And so the floor of your room accelerates upwards the floor accelerates up and hits this ball, which was not accelerating. Floor accelerates up to hit the ball. So the ball, from your point of view, appears to be accelerating down, but it's really the floor that's accelerating up. So ball appears to be accelerating down, but it's really the floor accelerating up. Okay, so I'm going to take pause here for a little interlude here. So I want you to remember Galileo's famous experiment. Okay, so Galileo's famous experiment was, yes, if I take two objects of any mass, different composition, whatever, and I let them free fall, I observe that they accelerate down with exactly the same acceleration. This was a total mystery. Okay, so Newton tried to explain this mystery, okay, with several paragraphs in his Principia, and tried to explain this weird fact about gravity. All of those explanations were ultimately wrong. The true explanation is that really what's happening is we've got these two objects, and as soon as you release them in free fall, there are no forces acting, and the ground accelerates up to hit them. So obviously, no matter what these objects are made of, or they're different masses or whatever, these two objects are going to hit the ground at the same time because the ground is accelerating up and hits them. Okay, so that was a brilliant stroke of brilliance from Einstein. Okay, so anyways, the point here is you can explain everything to do with gravity, like weight, the weight that you feel for something, and the apparent acceleration down. You can explain all of that without introducing or making up this new thing, this force of gravity pulling down, because acceleration up exactly mimics force of gravity down. So let me write that over here. Acceleration up mimics force of gravity down. Okay? So Einstein was looking for a new model of gravity. This fact that if you're in a room that's accelerating up, it will mimic all the effects of being sitting on the Earth with a force of gravity pulling down. That fact was far too much of a coincidence to ignore. Super important. Okay? So Einstein was really excited about this. This is what his happiest thought of his life kind of thing, right? Anyways, so we got that. So now let's go back to this picture, so take this picture from Einstein's point of view. Okay, so now we've got, what do we have? Okay, so we've got time here, time axis on the right, going to the right, space axis going up. And in this picture, okay, we'll start with Alice. So in this picture, Alice starts here, okay? Now, from Einstein's point of view, so Alice is in free fall. So Alice is like this thing right here in free fall, right? And so in free fall, her true acceleration is 0. The acceleration is 0, the force is 0, means that this should be a straight line trajectory through space-time. So Alice in free fall should be on a straight trajectory through space-time. So she starts off moving to the right like this through space-time, and she should continue to move to the right on a straight line. Okay, so her acceleration is 0. Okay, look at this thing. The acceleration is 0. There's no forces acting. The acceleration is 0, and so it must be that she is moving on a straight line, straight path through space-time. Okay. The trouble is, if she's moving on a straight path through space-time, how can she possibly move down to the bottom of the ladder? Won't you just stay at the top of the ladder? That's the trouble. Okay, so how do you stay straight? Stay straight, but move down. Okay, that's the trouble. This is a brilliant idea. Equivalence principle is brilliant, but huge and obvious problem. How can you stay straight? We want a straight line and yet still make it to the bottom of the ladder. Okay? Here's Bob. Okay, so Bob starts off moving to the right like this. Okay, but Bob is like this guy. Okay, he's sitting on the ground. He's sitting on someone's hand like this, and that hand or the ground is pushing up on him. It's like that spring, that compressed spring is pushing up on him. Okay, and so there's obviously and truly a force pushing up, but there's no other force according to Einstein. There's only an upward force, and so Bob should be accelerating up. Acceleration up means that his path through space-time should curve up. Acceleration up because there's a real upward force acting on him, the normal force, and no other force. So his path should curve up. Okay, so it should do this. And yet that's kind of weird because we know that he has to stay at the bottom of the ladder. It should be like this, kind of, but it also should be like this. So how do you reconcile this? So the problem here is how do you curve up or accelerate up, but not go up? So curve or accelerate up, but not move up. That's the crucial thing. Okay, so so great. I hope that kind of makes sense. We're now at a serious dilemma here. Okay, so we need to figure out how is it that we can, like, what's gone wrong here? This is such a brilliant idea. Is there a second brilliant idea in Einstein's little brain that will resolve this this discrepancy, this serious problem? And the answer is yes. And the answer is extremely simple. You'll like smack yourself in the forehead when you realize the answer. It's so dead simple. What he said is, just like, we make assumptions in physics. We assume that, oh yeah, in free fall, when something's free falling down, it's accelerating down. Oh, that assumption turned out to be wrong. Okay. We also assumed here, when we drew this picture of Alice's path and Bob's path through space and time, we drew the picture on a flat surface because pieces of paper usually lie on flat tables, right? And so we just drew it like this, but underlying this is this assumption that space-time is flat. Does it need to be? Might it not be flat? Might it be curved? Might it be that if we drew this picture instead of on a flat surface, if we drew it on a curved surface, would we resolve this discrepancy? And the answer is a resounding yes, and it's beautiful. Okay, so this is, let's try to resolve this problem by considering curved space-time. Okay, great. So how are we going to do this? We want to take this diagram right here and draw it not on a flat surface, but on a curved surface. Well, what kind of a curved surface? Oh, I don't know. I've got one right here. I've got an exercise ball, which is a curved surface. The surface of a ball is curved, and I've reproduced my diagram on this curved surface. So what I've got is the space axis is going up like this, the time along a line of longitude, and the time axis is running along a line of latitude. Great, that's t for time there. Okay, so I'm going to draw my space-time diagram instead of on a flat surface, on a curved surface, and this is the ladder that Alice is falling down in the first snapshot at t equals 0. This is the ladder she's falling down in the middle snapshot. This is the ladder she's falling down in the final snapshot at t equals 2 seconds. Okay, so now here's the thing. What Einstein says is that when Alice falls from the top of the ladder in the first snapshot to the bottom of the ladder in the last snapshot, we need to connect the dots with a straight line because her acceleration is 0. There's no forces. It's got to be a straight line. Well, let's just do that. Let's see what happens if we do that. Okay, so what we're going to do is we're going to take a little strip of tape here, and we're going to connect the top of the ladder in the first snapshot with the bottom of the ladder in the last snapshot, we're going to connect that with a straight line, okay? So you'll notice that we're going to start in the horizontal direction, like this, perpendicular to the ladder, okay? And we're going to continue to move in a straight line. By straight line, I mean the strip of tape that we put on the ball lies flat. I mean, imagine a table. If I have a table and I want to lay a straight line, I will just take a strip of tape and make sure the tape lies flat without crinkling. So this is a straight line. Another way to say it is I could take a piece of string and I could connect it between this point and pull tight like this. And that string will lie right, and so then I'll have the path of shortest distance between this point, and it will lie right along here. This is the path that airplanes fly from New York to London. They fly on straight line paths on a curved surface. They're called geodesics, okay? So by every measure, this thing here is a straight line. Okay, so it is a path of shortest distance between 2 points. It is a path that if you were to walk along this path with maybe this was the surface of the Earth, you would walk along it with 2 skis, always keeping the skis parallel to each other and so on. This is a straight line. This is a line with 0 acceleration. This is a line with 0 force. So Alice can start moving in that direction and continue to move on a straight line path and still make it to the bottom of the ladder. Okay, it's brilliant. Okay, and moreover, I want you to notice. Sorry, my little arm of my lamp is in the way of my face here. But I want you to notice something super important. Where in the middle snapshot, where is Alice on the ladder in the middle snapshot? Is she here? Is she here? Oh no, she's up here. She's above the middle. Remember that was a crucial observation that we made in our little experiment taking snapshots with Alice free falling. Now we can explain this fact now. We see that we can explain this important observation that Alice in the middle snapshot is above the center of the ladder. We can explain it in 2 different ways, 2 different models. One is a force model of gravity, to say that gravity is a force. Okay, so that means during the first half of her fall, she's moving more slowly. During the second half of her fall, she's picked up speed because she's accelerating down. Okay, and so during the second half of her fall, she falls farther. So we can explain this fact using by imagining that gravity is a force pulling down. But oh, isn't this amazing? We can explain this exact same fact by thinking not of gravity as a force pulling down, but as gravity as a curved space-time. So the mass of the Earth somehow curves the space-time like this, okay? And then we can explain this same fact, okay? So that's remarkable. Okay, so yeah. What else did I want to say? That's it. Okay, so now, yeah. So the crucial thing here is we've explained 2 things. This fact over here, using a curved space-time model, and the fact that Alice can start moving in the horizontal direction, but keep moving along a straight line and still move down to the bottom of the ladder. 2 brilliant things have happened here. Okay, so now let's wonder about Bob. So Bob, here, let me get rid of that little strip of tape there. Okay, so now Bob, in the first snapshot, Bob is at the bottom of the ladder. In the second snapshot, Bob is at the bottom of the ladder. In the third snapshot, Bob is at the bottom of the ladder. Let's connect his dots. Let's make his path through this curved space-time. Okay, so let me grab another strip of tape here. Tape is giving me trouble. Okay, there we go. Okay, so this is going to be Bob. What is his path in space-time? What can we learn from that? What will we discover here? So Bob's path through space-time is along a line of latitude. Okay? So let's put it on this line of latitude here. Do this carefully. Let me turn this towards myself so I can do it carefully. Okay, so great. So that's Bob's path. Now, what do we notice about Bob's path? Well, let's see. I'm going to try to make this tape lie flat on the surface of this ball. Oh, wait a minute. I can't make it lie flat. Look at that. It crinkles. Can you guys see those crinkles? So it crinkles. Where does it crinkle? It crinkles on the top of the strip of tape, not on the bottom. Okay, so what does that tell you? It tells you that the length of the line at the bottom of the strip of tape, if we follow along the bottom, that's got some length. Okay, but the length at the top is less. Okay, and so the tape has to scrunch up, and that's what happens when you try to put a piece of tape down on a curved line. So this line, because it's crinkled on the top, is actually curving up. Now let me try to convince you of that another way besides the crinkling of the tape. I want to compare Bob's path through space-time. I want to compare that with a straight line, and then you will see that Bob's path is actually curved, and it is actually curved up. Okay, so how do we do that? Well, we take another strip of tape, and we start in the same direction initially, but instead of following a line of latitude here, we're going to follow a straight line. So I'm going to lay the strip of tape flat. So this line here, the one that I just put on, this one is a straight line. It is a geodesic. This is how an airplane would fly going from New York to London. Okay, this is a path of shortest distance between that point and that point. This is straight. Well, let's compare this straight line, or let's compare Bob's line with this straight line. Oh, look what happens. We see that Bob's line curves upwards. Okay, and it curves upwards, in fact, like times squared. This is a quadratic curve here going upwards. So Bob's path through space-time curves upwards, which means he is accelerating upwards. And that's consistent with the fact that he's standing on a spring, and that compressed spring is exerting a force on him in the upwards direction. So this is amazing. So what it means is that Bob just standing on the ground doing nothing, he is constantly accelerating up without going up. Look, his position in space here, this is his position, this is the space axis. His position, his distance above the time axis never changes. He's not moving up in space, and yet he's accelerating up. He's accelerating up constantly without moving up. So acceleration up without moving up is sort of what the magic of space-time does for you. Okay, so that's remarkable. So now we have solved the objections to Einstein's idea. Let me put this up here. Okay, so remember, the equivalence principle was the first stroke of genius. Okay, Einstein recognized that, oh, if you're in a room that's accelerating up, all of the quote unquote gravitational effects that you experience are exact like weight, like when something is in free fall, it appears to be accelerating down. All of those effects of gravity can be explained. You can explain these things either by a force pulling down on things, or you can explain it by no force anywhere, but the room that you're in accelerating up. So Einstein would like to say, the room that we are standing in right now, the room that you are sitting in or whatever, that room is accelerating up. Okay, but that's kind of absurd because it's not. Well, is it? Well, so you have to understand what acceleration is. Okay, so acceleration is just a curved path through space-time. When there's no acceleration, it's a straight path. When there is acceleration, it's a curved path. Okay, and so so here's the curved path. So Bob is constantly accelerating up without going up. Okay, so great. And that's consistent with the fact that there is a one real force acting on him, okay, the ground pushing up, that normal force. Okay, so let me say one other thing, a couple of other things here. So in Newton's model of gravity, when we take an object and we throw it up and it comes back down, we explain that using a force pulling down model as follows. We say, oh yeah, this thing starts with some velocity in the upwards direction. Oh, but there's a force pulling down that's causing a constant acceleration down. And so on the way up, that's reducing the speed eventually to zero, and then increasing the downward speed. Okay, so we can explain this kind of up and down motion of a ball tossed up using a force pulling down model. How would throwing this ball up and coming back down look in the curved space-time model of gravity? Well, I don't know. Let's see. At t equals 0, we have to start at the bottom, okay? And then at t equals 1 second, it's up here. And then at t equals 2 seconds, it's back down here, okay? But according to Einstein, when we are throwing it up, when we are accelerating it, oh yeah, we're pushing on it, there's a force on it. But the instant it leaves our hand, and it's in free fall, first on the way up and then back on the way down, the instant it leaves our hand and it's in free fall, its acceleration is 0. There is no force acting on it. Its path through space-time should be a straight line. Let's see, is it? No. So what we want to do is we want to connect this point in, like at t equals 0 down here. We want to connect that with t equals 2 seconds down here. So we want to connect this point, t equals 0 at the bottom of the ladder, to this point, t equals 2 seconds at the bottom of the ladder. We want to connect those 2 points with a straight line. Well, let's do that, see what happens. Okay, so we start down here at the bottom of the ladder at t equals 0. We throw the ball up, and then it comes back down at t equals 2 seconds, and it's a straight line. So let me try to see what I'm doing here. Okay, there. This is so awesome. Okay, so this is a straight line. Well, if I get that exactly right. But this is a straight line. The tape does not crinkle here. Now, it crinkles a tiny bit because I put it on a little bit crooked. Or whatever. This is a straight line. So you can see that this line here, we're looking at this line now. This line here is a geodesic. An airplane would fly from New York to Paris along this straight line path. It's a geodesic. Okay. Now, what does this straight line path do? Well, from the point of view of Bob sitting at the bottom of the ladder, what he sees is first the ball is at his location. A little bit later, the ball has risen up. A little bit later, the ball has risen up high. Now it's at the peak of its trajectory. Okay, and then the ball starts coming down, coming down, coming down, right? And so we can use the curve, we can use either a force pulling down model, or we can use a curved space-time model of gravity to explain this, tossing a ball up and then coming back down. Okay, so that's kind of cool. Okay, so I want to emphasize a point. Okay, we have about 12 minutes left. I think we're doing not too bad for time. Okay, so so I want to re-emphasize this point. The key observation that we make about gravity, about our experiment of Alice free falling from the top of the ladder, the key observation we make is that in the middle snapshot, she is above the middle of the ladder. So that can be explained either by thinking of gravity as a force pulling down, or thinking of gravity involving no force whatsoever, and it's curved space-time instead. I want to emphasize, I'm not saying that gravity does not exist. I'm saying gravity exists for sure, but there's two models we're comparing. Is it a force pulling down on stuff, or is it a curvature of space-time? Is it the Earth, the rocks of the Earth pulling down on stuff, exerting this mysterious invisible force? Or is it the rocks of the Earth, the mass of the Earth, curving the space-time in the vicinity of the Earth? Inside the Earth and outside the Earth, curvature gets less as you move further away from the Earth or whatever, that kind of thing. Is it a force pulling down or space-time being curved? Both models work is the first important point here. Okay, so that's great. Okay, so we've got now two models. Okay, but how do we differentiate between those two models? So how you do that is you look for a prediction of something that's different. So is there something that the force pulling down model of gravity makes a different prediction for compared to the curved space-time model of gravity? If that's the case, then you can just do an experiment and you can see which one is wrong. Because in science, physics, we don't prove things to be right. We can only prove things to be wrong. Okay, so when our theory disagrees with the experiment, then the theory is wrong. Okay, when the theory agrees with the experiment, we garner support for the theory, and the more experimental tests it passes, the greater confidence we have, and then it changes from just a hypothesis to like a theory. Okay, so a theory is a very powerful thing. Okay, so anyways. Is there something that the force model of gravity would make a different prediction for than the curved space-time model? Well, you can see it right in this picture. Okay, so if we say Bob, so Bob is sitting at the bottom of the ladder. Here he is sitting at the bottom of the ladder. Maybe I should get rid of some of these. Getting a little bit messy here. Too many strips of tape here. Okay, so that was the straight line that we compared Bob's curving up line to, and this was the ball that we tossed up and down. So now we're just back to Bob here. Okay, and so we say Bob is standing at the bottom of the ladder. Okay, so time is ticking for him. Tick, 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 tick. While that time is ticking, tick, 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 Alice is falling. Okay, so we asked the question, from Bob's perspective, how much time did it take for Alice to fall from the top of the ladder to the bottom? Well, time is this axis. Time is in this direction. Time is the geometrical length of this strip of tape. Okay? So then we say, great. Let's look at this from the point of view of from somebody else's point of view. Let's take the point of view of not somebody at the bottom of the ladder, but someone's sitting at the top of the ladder. Okay? So from the point of view of someone sitting at the top of the ladder, how much time does it take? Well, we just need to connect these dots here with someone sitting at the top of the ladder. Okay, notice that this is definitely a curved line. Look at how crinkled that piece of tape is. This is definitely curving up. Okay, and so you see, well, the amount of time elapsed for or reckoned by someone at the top of the ladder is the length of this strip of tape. I wonder how the length of this strip of tape compares to. Oh, they're totally different. Okay, so from the curved space in the curved space-time model of gravity, time moves at different rates depending upon height. Okay, whereas from the force model or within the force model of gravity, obviously someone's sitting at the top of the ladder and someone's sitting at the bottom of the ladder. I mean, go back to this picture here. Okay, so someone sitting at the bottom of the ladder says, "Oh yeah, 2 seconds." Someone sitting at the top of the ladder says, "Oh yeah, 2 seconds." Okay, so there's no difference. So the force model of gravity says time moves at the same rate at the bottom of the ladder as at the top of the ladder. From the curved space-time model of gravity, it makes this wild new prediction, totally unexpected, that time, if gravity really is this, if gravity really is curved space-time, we could test that because the rate at which time moves up here is different from the rate at which time moves down here. And so you just run the test. And so you just take 2 atomic clocks, you stick one at the bottom of the ladder, stick one at the top of the ladder, wait all day, and then at the end of the day, look how much time has elapsed for these clocks. And you'll find a different amount of time. So right away, that rules out the force model of gravity. The force model of gravity makes the wrong prediction. Okay, and so right there, so plus a bunch of other tests that it fails, means that the force model of gravity is now scientifically obsolete. It's like J.J. Thomson with the plum pudding model of the atom. Yes. The atom has a bunch of negatively charged plums sitting inside some positively charged pudding. Well, that failed. okay, with Rutherford, showed that totally failed, right? And so those were models that were discarded because they failed experimental tests, okay? Now, here is a simple experimental test you can do. The IQC down the road, it's got atomic clocks accurate enough to do this experiment, okay? And this experiment is done a million different times, okay? So the force model of gravity fails. It's now scientifically obsolete, okay? And in fact, there are many other experiments where the curved space-time model of gravity has passed those experimental tests with flying colors, okay, which adds support to our confidence that the curved space-time model of gravity might be right, okay? Whereas all of those tests, Newton's force model of gravity has failed them all, okay? So force model of gravity is obsolete, okay, for sure. Now, how long general relativity, how long curved space-time model of gravity will survive, who knows? Okay, so anyway, so other experimental tests are the bending of light. So Newton's model of gravity predicts a certain amount of bending of light, say when a ray of light passes near the sun. Okay, and Einstein's model of gravity predicts a certain amount, which is exactly twice the amount. So you run the experiment and you find that it agrees with curved space-time model and definitely does not agree with force model. So force model ruled out. There's Mercury's orbit. So we talked about Mercury's orbit at the beginning, a discrepancy. Well, this curved space-time model of gravity brilliantly resolved that discrepancy and explained that extra bit of precession of the perihelion of Mercury's orbit. Okay, another win for gravity, another loss for force model of gravity. Okay, the Newton's model of gravity does not predict gravitational waves. There's just this weird instantaneous action at a distance. Okay, whereas Einstein's model of gravity is so Newton's model of gravity is just like electrostatics. Einstein's model of gravity is kind of like electromagnetic, like electric and magnetic fields. There's sort of electric gravitational effects and magnetic gravitational effects, and they combine together to give gravitational waves, like it's a causal field theory. Okay, and so it predicts gravitational waves. Newton's theory does not. Okay, and then, as you all know, a couple of years ago, LIGO brilliantly made a detection, the first detection of gravitational waves. It was really hard to do. It took 100 years of technological development, but humans finally did it, and they detected it. So another win for gravity, another fail for force model. Black holes. And the severe bending of light around black holes and so on. So as you know, the Event Horizon Telescope, and Avery Broderick was a key member of that team in our department. They just recently imaged a black hole, right? That's the most direct evidence we have for black holes. Newton's model of gravity doesn't say anything like that, right? And so, for sure, the force model of gravity is obsolete, scientifically ruled out. And this is the best model that we've got, okay? And so I'm hoping that you'll kind of look at this, you'll think about it. I know it's thinking outside the box, but I just want you to experience the brilliance of Einstein. These two brilliant things that he did. The first one, equivalence principle. So understand how a person standing in a room that's accelerating up with no gravity anywhere, no gravitational force anywhere, can exactly mimic what's happening for a person standing on the surface of the Earth, where we imagine the Earth is exerting a gravitational force downwards. So understand this equivalence principle. Understand that this is a serious problem. Einstein is saying that the room we are in right now and the chairs we are sitting in and everything is accelerating up, okay, without moving up. How the heck is that possible? You just curve the space-time. We've always assumed that space-time is flat, okay? Or actually before special relativity, there wasn't even a sort of a concept. And then with special relativity, Einstein realized that without gravity, space-time is flat. And then with gravity, well, what is gravity? Well, you just take that flat space-time and you curve it. And then that gives rise to all of the effects we call gravity, okay? Awesome. Oh, one last thing. Oh, 1:30, okay. We're going to go over time for about 2 minutes because this is a super important last sort of demo of this, okay? So this is a lot of fun. All right. I'm going to turn off the light a little bit. Okay. And I'm going to turn on this little accelerometer that I have here. Okay. So this is, I hope you can see this here nicely. So this is an object. This is a device, an electronic device, which measures acceleration in that direction. You see the green arrow there? It measures acceleration in that direction. If the acceleration in that direction is positive, then green lights go on. If the acceleration in that direction is negative, so in other words this way, then red lights go on. So this is acceleration in that direction positive. This is acceleration in that direction negative. Okay, so if I take this accelerometer and I were to move it from here to here, then when I first start moving it, there's acceleration in the positive direction. It's picking up speed. So the green lights should turn on. And then in the second half, when I bring it to rest at this point, then its acceleration is negative. It's in that direction. So the red lights should go on. So when I move it from here to here, it should go green light, red light. And when I move it back, it should go red light, green light. Okay, so let's see if this works. So pay attention carefully to this thing. The angle is kind of awkward here. Okay, anyways, okay, so let's do it. So what did you see? Green light, then red light, right? When I do this, when I bring it back, it's red light, then green light. Green, red, red, green, green, red, red, green. So this accelerometer works, okay? It's this amazing thing. So it measures this acceleration along this direction. Now remember, what did Einstein say? Einstein said, the gravity is curved space-time, and the curved space-time is such that the effect of the curved space-time is to make it so that this room that I'm in, the room that you're in, and so on, that room is accelerating up without going up, but it's accelerating up. I have an accelerometer here. I wonder how I could test Einstein that everything in the room here that's at rest in the room is accelerating up. Well, this thing measures acceleration in that direction. Let's just turn it like this. Ooh, look at that. This thing now to get those accelerated like right now, according to this instrument which measures acceleration, is accelerating up, okay, without moving up. That's the magic of curved space-time, okay? And then another thing that Einstein said is, so it is when the apple is on the tree limb, like this, hanging from the tree limb, that it is accelerating up, because there's only one force acting on it. The tree limb is pulling it up like this, causing it to accelerate up along with everything else, okay? And it's precisely when the apple is in free fall. It's precisely when I let go of this thing and it free falls down. Precisely at that time, the acceleration should exactly drop to zero. So when I drop this thing, according to Einstein, all the lights will go out. Let's see if this works. Slow. Okay, but during that free fall time, I mean, I can see it here, but it's too fast, maybe a little bit for the camera. But as soon as you drop this thing, the instant I let go, all the lights go out. And then as soon as I catch it, all the lights go on again. All the green lights go off, and then they go on again. Okay, so while it's in free fall, no lights are on. There's no acceleration. So what Newton got wrong was the assumption. He just assumed that when things are in free fall, they are accelerating down. He got that backwards. It's precisely when they are up in the tree, the apple is in the tree, and everything around us at rest on the surface of the earth, that's when they're accelerating up, okay? So, yeah, I think that's basically about it, and we're about 4 minutes over time. So yeah, I hope that was a little bit illuminating and somewhat fun. I should also say about this accelerometer, right? Certainly, this agrees with what Einstein says. But I'll ask you as sort of a challenge: you can also explain this result using the force model of gravity. Okay, so I don't want to mislead you, but it's pretty remarkable. Okay, so I challenge you to think about that, how an accelerometer works, and how you could explain it using the force model of gravity as well. The other thing, I guess, to say is that you know, this thing, that we call this gravitational force. You know how especially in high school physics teachers like to poo-poo, fictitious forces or forces that arise in accelerated frames of reference. Well, I, I sort of, that's unfortunate because you can see that the key step, this equivalence principle, the way that Einstein got from Newton's force model of gravity, the first big stepping stone was to consider and accelerated the quote unquote fictitious forces that exist in an accelerated frame of reference, right? Like this guy in this frame of reference, that in this accelerated frame of reference says, oh yeah, I'm certainly exerting this normal force up. That's real, right? And but if I take the point of view that I am not accelerated, right, then I would have to invent this fictitious downward force to explain to get zero net force and to explain my zero acceleration, right? So this is an extremely powerful um, um, idea, and it rests squarely on considering quote unquote fictitious forces in accelerated frames of reference. Yeah, and I should say something else here on that note here. So people wonder sometimes, well, how did Einstein come up with general relativity in the first place? Like, what got him to suggest this idea of curved space-time? Like, did it just like pop into his head at random? Like some kind of like, no. It came as follows. This is called Einstein's, the missing link in Einstein's thought process. And it's a really beautiful thing, beautiful thought experiment. So what you do is you do this. You say, you have a rotating platform, which we're going to view from the top down. Okay? And we're going to imagine that we've got a bunch of Alices inside here, and we've got a bunch of Bobs outside here, and so on. So these are Alices, and these are Bobs. And the Bobs are in an inertial frame of reference, and they are going all the way around just immediately outside this rotating platform. And the Alices are inside a rotating frame of reference, so a non-inertial reference frame, okay? And this non-inertial reference frame is rotating like this, and so all the Alices are rotating, okay? Now, the first thing to say is that these Alices, they experience, an artificial gravitational force. They feel an artificial gravitational force down like this. Okay, so for them, up is towards the center of their rotating platform. So this is an artificial gravitational force down that they experience. Okay, I'm sure you all can appreciate that. If they're holding an object in their hand, in order to keep that object in their hand, they're going to have to push upwards like that, because that object, as it moves around and around with them, is actually accelerating towards the center of the circle. Well, there has to be a force pushing on that object towards the center. And so this Alice, holding that rock in her hand, needs to push up towards the center in order to support the quote unquote weight of this object. So these Alices are experiencing, in this non-inertial reference frame, are experiencing a fictitious gravitational force down. Okay, so Einstein said, look, great, I'm trying to find a new model of gravity, right? So here's artificial gravity. So I want to say in quotes, here is artificial, here's artificial gravity, okay? what are the effects of this artificial gravity? So what he did is he looked at this situation in the context of special relativity. So this is, so in the context of special relativity. And so when you do that, you notice two things. First of all, there's time dilation. That's time dilate. I can't spell today. Time dilation. Okay, so time dilation. So what that means is these bobs here, they have clocks. They each have clocks, and they're all synchronized with each other and so on, and they're ticking away, tick, 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 tick. These Alice's, they also have clocks. Okay, and so, but when Alice's clock is moving by, or when Alice with her clock is moving by any one of these bobs, she's moving relative to him. Okay, and so he will look and see, oh, her clock is running slow. And so, first of all, what you recognize is that these Alices who are in this artificial gravitational field are actually also experiencing time dilation relative to these guys. So there's time dilation. And so time dilation associated with an artificial gravitational field, at least. Okay, but there's also length contraction happening. So these Alices, suppose that the inside circumference, just on the inside, is 100 meters around, and the outside circumference is 100 meters around. And suppose that the Alices and the Bobs, the width between their shoulders is exactly 1 meter. So you can exactly fit 100 Alices around the inside, and you can exactly fit 100 Bobs around the outside. Okay, so but now when an Alice, and so an Alice has this shape, okay, and when she's at rest, she's 1 meter wide. Okay, and here's a Bob, looking at that Alice. He's at rest in this inertial reference frame. She's moving like this now. But if she's moving, then when he takes his two hands and touches both of her shoulders simultaneously and says, what is her width in my frame of reference? Well, it's going to be less. And so the Alices are going to be like this. And for this Bob who was right next to him, he was looking at this Alice. Okay, and so he reaches out and touches both of her shoulders simultaneously and notices that in order to do so, he has to put them further in. And so the next Alice is this wide, and so on as you go around. And so what you notice is there's 100 meters around just the outside circumference, but as this platform starts rotating faster and faster and faster, you could actually fit more Alices in. Okay, and so as far as the Alices are concerned, spaces, gaps open up between them. They're still 1 meter. From their point of view, they're still 1 meter wide. Okay, but now these gaps appear between them. And so it's more than 100 meters on the inside. And so there is a warping of space. So let me say this a little more clearly. So special relativistic time dilation gives rise to a warping or warped time associated with this artificial gravitational force. Special relativistic length contraction is accompanied by warped space. Okay, so the actual amount of space inside this rotating platform is larger. Like if you had a tin can like this and it's got some volume, 1 liter, and you open up a little hole here and you pour it and you fill it up and there's 1 liter in there now. Great. Now you start spinning the thing faster and faster and faster. The amount of volume inside for someone rotating with that, the amount of volume inside is larger. Okay, and so when that water starts moving at that same rate, if the water is spinning at the same rate as the can, okay, then there's more volume inside, and so you could fit more water. So when it's spinning fast, you could add more water, keep adding more water, 1 liter, 2 liters, whatever, right? Actually, there's a limit. It's not like an infinite amount, okay, even when the outside edge moves at the speed of light. But there's more volume inside. So there's a warping of space also associated with this artificial gravitational field. So this was the key thought experiment. So Einstein considered accelerated observers. Okay, Alice is an accelerated person. He considered accelerated objects and accelerated frames of reference within the context of special relativity and discovered that those accelerated frames of reference, which are associated with artificial gravity, are also associated with warped time and warped space. And then, being the smart guy that he was, he put two and two together and said, maybe real gravity has something to do with warped space and warped time. That was the real step, like the mental step that Einstein took to get from, to resolve this problem here and get to this picture of curved space-time. And I'll just thank you for coming out, and this will be recorded, so that's good. So for those of you that didn't quite make sense or whatever, there's parts that didn't make sense. I encourage you to maybe just watch the video again, because at the end of the day, it's actually really quite dead simple, but it's a weird way of thinking. So it's sort of like those Gestalt pictures, which are, well, I can't draw one, but there's the two vases, and then they look like a face or whatever. Like, okay, this is a terrible thing, but anyways, you can think of it as two vases or a face or whatever, right? And so at one moment, sort of, it looks like vases, but then you stare at it for a while, and then it flips to looking like faces, and so on, right? That flip back and forth. So this flip back and forth between these two different sort of pictures is exactly like the flip back and forth between thinking of gravity as a force model and thinking of gravity as a curved space-time model. So once you just need to sort of practice that flip back and forth, right? I guess another thing to say that's important that I didn't say so far is that while the force model of gravity is wrong, like it's really wrong, like it's completely wrong, okay, it still works. It works extremely well. So for anything that happens, say, within our solar system, so let me just write down something here. So this number is super important. Okay, so if you have any like amount of mass within a radius r, and you calculate this number, 2 times g, Newton's gravitational constant, times the mass divided by c squared r. If you calculate this number and you find that that number is much less than 1, then Newtonian gravity is just fine. It'll give you predictions that are as accurate as to the extent that this is much less than 1. Okay, it's only when this thing starts to become not much less than 1, but comparable to 1. So for instance, when it's equal to 1, then this means you've got a mass m within a radius r, such that r is the Schwarzschild radius, and you have a black hole. And then you need Einstein gravity for sure. Okay? So to the extent that this number is really small, Newtonian gravity will give you good predictions. It's totally wrong in principle, but it'll give you the right answers, more or less. Okay? But as this number gets bigger and bigger, it'll give you wrong answers. And you really need to go to Einstein. And so this happens in two general cases. It happens in the case of relatively compact objects, like black hole being the most extreme, but neutron star and to some extent white dwarfs. Okay, you need to start using general relativity, and at the other extreme, you need to start using general relativity when you are dealing with cosmology. Okay, so Newtonian ideas of cosmology work pretty well when you're relatively local. But when you start considering sizes of space comparable to the observable universe, then this number here, this is the mass in the observable universe, this is the radius of the observable universe, this number becomes comparable to 1. So it's telling you that Newtonian gravity can't explain cosmology. You need general relativity. Okay, so sorry, I got sidetracked there. If you take a look at the solar system, anywhere in the solar system, where is gravity the strongest? Well, it's strongest at the surface of the sun. So if you take the mass of the sun in this formula and you divide it by the radius of the sun here, then this number will turn out to be on the order of 10 to the minus 6, which means that all of your calculations based on Newtonian gravity are accurate to like 1 part in 10 and 1 part in a million. So that's pretty accurate, right? And so it's certainly good enough to put people on the moon, okay? And it's also good enough to get to most of the planets. The only place where you really had to take into account this very small discrepancy, or the main place that I can remember, was with what was it called? There was a mission to Mercury. So Mercury is pretty close to the sun, hard to get to, and the gravitational fields are of all the planets are strongest, for the planet Mercury. And so there you had to actually make use of general relativity in order to accurately get that. I think it was called the messenger mission. Get the messenger probe to orbit. First of all, to reach Mercury and orbit it accurately. You had to use general relativistic effects, but but anyways, NASA, Jet Propulsion Laboratory, JPL, they have a super detailed computer model of all of the objects in the solar system. Okay, so that's all the planets and all the thousands and thousands of asteroids and all kinds of stuff. So they have everything in there in a database, and that entire database runs with a general relativistic version of the solar system with a curved space-time model of gravity. So it's making this better than 10 to the minus 6. Right? It's making it better accuracy. And you need that over long periods of time because small errors build up and build up and build up. So you need it as accurate as possible. And so when, NASA is thinking about launching, missions out to Pluto or whatever, or wherever, you need to know this, whatever, you need to know you need to understand with great precision the orbits of all the objects in the solar system, and that actually is using GR. Yeah. Okay. So yeah. So again, thank you guys for coming out, and thanks again, Gabriel. This has been a lot of fun. You could see I could yak about this stuff all day long. But so everyone, take care and have a great rest of your day. All
You
right.
too.
You as
So,
well, Dr. Ebb.
thank you.
Have a good
All
day,
right.
Dr.
Bye
Ed.
for now.
Have a good
Thank
day,
you.
Dr. Ebb.
Thank you. You guys are awesome. Thanks for coming.